Okay, so in this lecture, we're going to do a simple machine learning example just to show you kind of what we do in machine learning and what a machine learning script is meant to do. Okay, and the reason we're doing this is because we're basically going to go through this process in all of my machine learning courses. And remember that this course is a prerequisite to those machine learning courses. So if you want to understand the process we're taking in my more advanced courses, then you can watch this to really just understand the steps. Okay, because the whole point of this is to understand those steps. There's not going to be any complex algorithms you have to learn, no complex syntax. This is purely to learn these steps in preparation for more advanced lectures where you do learn those algorithms and learn how to write that code. Okay, so one important thing to keep in mind is that this is meant to only represent sort of a single iteration of what we do in a machine learning project. Okay, so when we're in a course and you're learning about an algorithm, we're not really going through a whole life cycle of a machine learning project, right? So to give you an example, if this was a real life project, you probably wouldn't only test a single model, and you would probably do a lot more work in terms of choosing certain parameters, running cross-validation, in order to be more careful about predicting how your model is going to perform on unseen data. Okay, so there would be a lot more steps in a real-world project that aren't really relevant here and aren't really relevant in my courses, where the purpose is to learn an algorithm. So, for example, if you're learning about neural networks, then in that neural network course, your main goal is to learn about how to implement a neural network, right? It isn't to learn about the steps of a machine learning project, which is sort of orthogonal to neural networks. Okay, so those would be two separate courses, right? You'd want to take one course to learn about the operational aspect of machine learning, whereas it would be another course to learn about neural networks. And I see a lot of people get this confused, right? They'll take a neural network course and then expect to learn about these operational aspects of machine learning, which is not correct, right? These are two separate subjects. Okay, so that being said, here are the typical steps we will take in the machine learning script when our goal is to learn about a specific machine learning algorithm. Okay, so number one would be loading in the data. Once we have the data, we want to split the data into train and test. Okay, so, well, let's go back to number one. I want to explain a little bit more about that. So where does data come from? Well, typically you'd download data from the internet, in the case where you're using a data set that someone else has made. In some cases, you'd be collecting the data yourself. So you'd have to maybe talk to your coworkers about how that would be done. For example, if it's in a database, you'd need to know how to get the data out of the database. If you're a programmer like myself, you maybe already know how to do that. So that would be excellent. And in other cases, in some simple cases, as you'll see, some libraries such as Scikit-Learn, which is the one we're about to use, will contain functions to gather the data by itself. So you can just call a function, it will return the data in a format that's nice for you to use. Okay, so that's not what we're going to do in this course, but it will be an option in other courses. Oh, and just another quick note. As you know, there are two versions of the NumPy course. Okay, so there's the free version of the NumPy course and there's the paid version of the NumPy course for legacy reasons. You can read about that or ask me about it if you're unsure of the situation. But basically, because of certain circumstances, there are two versions of the course, a free version and a paid version. And the paid version already has a big long section about these practical aspects of machine learning, versus the free one does not, because it is limited to a 2-hour window on some platforms. Okay, so this video was made specifically for the free version, but I may include it in the paid version as well, since I want those students to get all of the material I made for this course. This free version is meant to be a much smaller example, just to show you the very basics. Okay, but if you want to go into more detail, of course, you can look at the longer version of this course. Okay, so that being said, sorry I got off track there, but we'll go back to step number 2, which is to split the data into train and test. Okay, so why do we want to split the data into two different data sets? And the reason, as you'll learn later in machine learning, is that it's possible to fit a model very well on the train set, but that also simultaneously does very poorly on data it hasn't seen before. Okay, and so we might call that the test set. So you'd want to make sure that your model works both for data in the training set and data that was not in the training set. Okay, and so there are some visual examples of this as well. I think the visual examples are a bit better to explain this concept, but there are no pictures in this lecture. Well, you know what? Let's just look at one, just for completion's sake. Okay, so here's a nice example of overfitting, underfitting, and a good fit. Okay, so we can see that the true pattern is probably something closer to this, whereas if you underfit, right, your model is not performing well on the training set, but it's also not going to perform well on the test set. So imagine all these data points. These are the data points in the train set. And a new data point would be a data point that follows this pattern, but doesn't belong to one of these existing points. Okay, so the underfitting case is where the model just doesn't fit well at all, right? It's not a good match to the training set. And if you gave it a new data point, let's say over here, that would also not be very close to the prediction. The prediction is this dotted line, by the way. Okay, so, and in this case, the overfitting case, you can see that the model prediction is very close to the actual data points. Okay, but remember, this is only for the train set. This is only for the data we have. Okay, and it's an even better fit in terms of the error than the good fit, the so-called good fit in the second example, right? So if you chose your model based solely on how well it does on the train set, you would choose this model because it has the least error. However, if you gave it a new data point, let's say the data point is right here. Hopefully you can see that. I don't know if it's going to show up in the video, but I'll mark it down in case it doesn't. But if the data point was right here, you can see that the model would have a large error because its prediction would be down there, okay? Versus with this model, it would be a little better. Okay, if the test point was here, then the model prediction is over here, which is not that bad. Okay? So that's the whole idea of training test sets. You want your model to perform well, not just on the data you have, but on data you're going to see in the future. Okay, and so why have I written validation here in brackets? Okay, so the reason for that, you'll learn this more in a future machine learning course that's more advanced, right? This is just the very basics. But sometimes we would like to use out-of-sample data to choose parameters. So suppose there is some parameter in our model that we have to hand tune, and we want to pick a value such that our model performs well on out-of-sample data. Okay, but if this out-of-sample data is used for that purpose, then really what we're using the data for is to validate our choice. So we call it a validation set. Okay, and then the true test set would be like the data set that your model has never ever seen before that we're actually using the model for. So for example, if we're going to deploy this model in the real world to maybe serve advertisements to users in the future, then that would be considered the true test set. Okay, the true test set is data we have really not seen before. Okay, and data in the future is an example of that because obviously you can't see data that, comes tomorrow or the day after or the day after. And so another example of that is predicting stock movements. Okay, so finance is a field where overfitting on the train set is actually pretty common. And obviously you don't want to do that because then you'll lose lots of money. Okay, so in finance, why is that such a great example? Well, because we want to predict tomorrow's stock movements, or we want to predict where stocks are going to go a month from now compared to today. Okay, so that's always going to be in the future. Okay, so that's enough for the train test split. Now let's move on to building the model. Okay, so building the model, you'll see that in this lecture, it's not going to be so complicated because we really just have to call a function. But in a proper machine learning course where you're learning about a specific machine learning algorithm, you're going to be learning how to build the model from scratch. Okay, so this is going to be easy in this lecture, but probably a bit more complicated in future lectures. Although in this list, what I'm really referring to is building an instance of an object that represents the model. Okay, so I guess in all cases it's going to be easy because really what you're doing is instantiating an object of the model that you want to build. Okay, and so the next step is to fit the model. Okay, so what is fitting the model? So I guess it helps to go back to this picture. So imagine that, you build your model is a line, say y equals mx plus b, but you don't know m, the slope, and you don't know b, the intercept. Okay, so the fitting process would basically be the process of finding what is m and what is b, what is the slope and what is the intercept. Okay, so that's what fitting is. Fitting is finding those model parameters. Okay, and obviously in future machine learning courses, you'll learn how that's done, but we're not going to discuss that in this course, which is more about code. Okay, so once we fitted our model, we would like to evaluate our model. Okay, and I guess that brings us back to this picture again. So evaluating the model, that's basically the process of figuring out, well, how well does this model fit? Okay, and so we're going to do that in this lecture, and we'll see how to tell how well this model fits both to the train set and the test set. Okay, so remember, we are keeping some data held out from the training process in order to use that to evaluate the model in the future. Okay, so that's sort of an emulation of how well the model will work in the future. And of course, it's not perfect, right? So for example, imagine data is non-stationary. It's changing over time. So suppose you build a model to predict stock movements, say from 2000 to 2020. Okay, and your model works very well on both the train and test data. Okay, so, or the validation data, depending on how you think of it. Okay, and so suppose the model works really well during that period, but then you hit 2020 and say COVID happens and maybe we have a recession or a depression or something like that, and the data is no longer following the same distribution as it was during the period of 2000 to 2020. Then your model might still perform bad on those future days. Okay, so that's the whole point of evaluating the model. We want to see not only how well does the model do on the train set, but also on the test set. And you'll notice how these three situations can be inferred from your model's performance on the train set and test set. So think of how the model would perform on this data set, the one on the left, if you can't see the mouse. In this case, the model would perform poorly on both the train set and the test set on the out-of-sample data. Okay, versus in the overfitting case, what you would expect to see is that the model would perform very well on the train set and very poorly on the test set. Okay, and so in the middle case, you might see, well, the model is going to perform relatively well on the train set and similarly well on the test set. Okay. Oh, and one thing that catches people off guard sometimes is that because of these pictures, let's look at another one that illustrates the point as well. Okay, so this is another example of a visualization of this underfitting and overfitting concept. Okay, so in this case, when we increase the model complexity, we tend to, so by model complexity, we sort of mean the amount of curves on this model. So as an example, we would say this line is not complex because it doesn't have any curves. And this squiggly thing is very complex because it has many curves, okay? So that's just sort of a proxy for how complex the model is, how many little curves it has. But you'll learn more about what we mean by model complexity in more advanced courses. Okay, so, well, what can we see from this? We can see that the training error decreases as we make the model more complex, which makes sense given that picture. But the test error increases. Okay, so my point was that this is an idealized picture. So what to not get caught off guard by is that sometimes the test error will actually go down more than the training error. So with a very complex model, your test error might be down here, even though the training error is up here. Okay, so that could happen. It's not always going to happen, but it's a possibility. Okay, so these are just generalized pictures meant to explain the concept, but it does not imply that this is what you're going to encounter every single time. Okay, and now step number 6 is to make predictions with the fitted model. Okay, this is not really something we always want to do in these machine learning scripts because most of the time it's pretty obvious, but it's a question I get a lot, so we will cover that as well. Okay, so now on to the next step. What is supervised machine learning? So there are different types of machine learning and different ways we can categorize it. So one way is supervised and unsupervised. In this lecture, we're only concerned with supervised learning, and we are only concerned with a specific type of supervised task called classification. Okay, so what is classification? So classification as opposed to regression. So actually, we've already seen a picture of regression. So regression is where we are trying to predict a numerical value. Okay, basically, we're trying to curve fit. Okay, so you'll sometimes hear statisticians who are very bitter about machine learning. They'll call machine learning glorified curve fitting. Okay, which is not completely untrue, but it definitely reflects that sort of bitterness that statisticians tend to have. Okay, so regression is when we're trying to predict a number. Okay, so compare that to classification, where we are trying to predict a category, a class. Okay, so we have some examples here in case that's not clear. Okay, so to describe it in general, we are given examples of input and target pairs. And what our goal is to try and predict the target from the input alone. Okay, so that's the general concept. And now let's go through some examples. Okay, so the first example is trying to predict whether a student passes their exam given only number of hours studied and a number of hours playing video games. Okay, so the inputs in this case are the number of hours the student studied and the number of hours they spent playing video games. And the output is a category. Okay, it's pass or didn't pass. Okay, so that's a binary category. And so you can also imagine what the data set would look like. Okay, so you can imagine it as an Excel spreadsheet. Okay, so I hope you guys have had a chance to use Excel in the past or something like it in maybe high school or middle school or something like that. You're basically storing data in a table. Okay, so you'd have one column for number of hours studied, another column for a number of hours playing video games, and another column for whether the student passed or didn't pass. Okay, so just picture an Excel spreadsheet in your mind, and that's how the data is represented and stored. Okay, so now example number 2 is to predict whether a stock will go up or down tomorrow, given indicators computed from the stock price's past time series. Okay, so we've all seen stock price time series, I think. If not, go look up the S&P 500 and you'll probably see a stock chart. Okay, and so from that stock chart, we can compute what are called indicators. Don't worry about what those are now. But just know that there's sort of different summaries of the time series that you can make. Okay, that will give you some idea of where the stock is going to go in the future. It's kind of controversial whether or not they actually work, but they exist. So I'm not making any claims about whether or not they're good. I'm just saying that they exist and people use them for this purpose. Okay, so we can predict whether a stock price will go up or down tomorrow. Okay, and so why is that classification? Because that's a category, up or down. Okay, as opposed to the regression case, and this lecture is not about regression, so this is kind of optional. But if we wanted to predict the stock return, its actual value, like 10% or 3% or minus 5%, that would be a number. So that would be regression. But we're doing classification. Okay, and so the final example here is to predict who will win the presidential election. And I haven't given you examples of any inputs, but as an exercise, you can think of what inputs might be useful to make this prediction. Okay, and so unlike these examples, these are binary classes because there are only 2 choices. this might be a multi-class problem because there might be more than 2 people running for president, okay? So hopefully that gives you a good overview of supervised machine learning and specifically classification. And so now we're going to move on to the actual code. Okay. So for this lecture, we're going to use the famous Iris dataset, okay? And so this dataset, I've given you the original URL here. So you can always visit this if you want to learn more, or if, say, my URLs are not working, you can go to this URL to see if this works. But in my experience, this URL actually goes down more often, which is why we're not using it. So if you try to go to this URL and it's not working, probably just try a few days later and it will work. Okay. And I also wanted to mention that this dataset is included in Scikit-Learn, but I wanted to show you a more generic example of how we do this process. And this is more generic because typically your data won't be included in Scikit-Learn and you'll have to load it from some file. Okay. And so you'll see here that when we download the dataset, we're downloading it from my website. So I've stored this data on my website. There are other ways to get data into Google Colab, including using your Google Drive, but we're not going to discuss that in this lecture. Okay, and so in order to download this data, we're using the wget command. Okay, and so just in case you don't know, we can use Linux/Unix commands in Google Colab or Jupyter Notebook as well. As a side note, if you prefix the command with a bang or an exclamation mark. Okay, so we're going to download these 2 files, iris.data and iris.names. And then we're going to run the ls command to see that the data has arrived in our local directory. Okay, you'll see that we have 2 copies because I had run this script just before making this lecture. Okay, but that doesn't matter. So if you run this just the first time, you won't see these with the .1 at the end. Okay, and so the first thing we're going to do is look at the .names file. So the .names file is sort of just information about the data set. Okay, so you can see here it has the title of the data set, the sources, past usage, relevant information. Okay, so you can read all that stuff if you like. But the more important stuff is over here. So this tells us the number of instances we have. I usually call this the number of samples. So we have 150 samples in total, and we have 50 samples for each of the 3 classes. Okay, so this data set is a 3-class data set. And as input into the model, we have 4 different inputs, 4 numeric inputs. Okay, and these are predictive attributes. Okay, so, and this tells us what the attributes actually mean. Okay, so the first 4 columns correspond to sepal length in centimeters, sepal width in centimeters, petal length in centimeters, and petal width in centimeters. Okay, so, well, it's worth talking about what this data set is in the first place. So this data set looks at iris plants. Okay, they're basically plants, and it measures specific attributes of that plant. So imagine like taking a ruler and measuring different parts of the plant. Okay, and using those measurements, we want to predict the type of the plant. Okay, so that's what we're calling the class. So there's Iris setosa, Iris versicolor, and Iris virginica. Okay, I hope I'm pronouncing those correctly. I have no idea, but you get the idea. Okay, so there are 3 different types of plants, and we're trying to use quantitative measurements of the plant to predict the type of plant that it is. Okay, so hopefully that makes sense. Okay. And now we're going to run the head command on the data set to see how the data is formatted. Okay, and so this is a very common format to use in data engineering, data science. It's basically a CSV. Now the file extension for this file is .data and not .csv, but it is still a CSV. Okay, so what defines this as a CSV is the format of the data, not the file name. Okay. And that's why later on we can use pandas.readCSV to load in the data, even though this does not have a CSV file extension. Okay, and so again, how is the data formatted? It's formatted as a table. And you could even, by the way, open this in Excel as well. Okay, so Excel might not recognize it because it doesn't have the CSV file extension. But if you renamed it .csv, you could probably open it in Excel. Okay, but you can see how it's formatted, where the first column corresponds to the first, what we call input feature or input attribute. And we have the second column, the third column, and the fourth column. So these are all the 4 measurements we were talking about. And then the last column, we have the class. Okay, and that's stored as a string. Okay. So the next step here is to load in pandas. Well, import pandas. So you've learned how to do that. And we're going to load in the data by calling pd.readcsv. And we're also saying header is none because there's no header here. Okay. So hopefully this is just review because we've done all this already. And so we're going to call df.head to see how the data looks like after it's in the data frame. Okay, so basically it's just a pretty version of the same thing we saw above. Okay, everything is at a table and we have the columns 0, 1, 2, 3, and 4, which correspond to the first 4 input features and the class. Okay, so now it's typical in machine learning to call the inputs X and the targets Y. Okay, so that's what we're going to do. We're going to split up the X's and Y's. And so what are we doing here? We're grabbing column 0, 1, 2, and 3. We're calling that X. And we're grabbing column 4, and we're calling that Y. Okay, so just remember that when we use pandas and we index it, it does not work like NumPy, right? So the square bracket notation selects columns, whereas in NumPy, this would initially select rows. Okay. So now we're just going to look at the data again. So when we call x.head, we can see the input features, and when we call y.head, we see the targets. Okay, and so just as a quick side note, when you're using machine learning models, machine learning typically works with numbers, right? Machine learning is doing mathematical operations, and a string is obviously not a number. So typically, if you're writing a model yourself, you would also write some code to convert these strings to encode them as numbers. And typically we would start from 0. So we would say, we would call this class 0, we would call this class 1, and we would call this class 2. Okay, so that's typically what we would do if we were writing the model ourselves in order for it to work nicely with our code. Okay, but in Scikit-Learn, which is the library we're going to use to do machine learning in this lecture, you don't have to do that because this conversion happens automatically within their functions. Okay, so it's already built in. You don't have to do it yourself, but when you're writing your own models, you will. Okay, so just keep that in mind. Okay, so now let me write an additional comment here. So this is n by d, and this is n. Okay, so why did I write that? Because in machine learning, so right now it's pretty trivial, but it will become more important when we look at more complex types of data like images and time series. We should always be thinking about and concerned with the shape of the data, okay? So as you can see, since it's a table, it has 2 dimensions. So we have 150 by 4. Okay, so as you recall, this corresponds to what we saw above, where it said there were 150 instances or samples in 4 attributes or 4 input features. Okay? And so typically the letters I use for these in my courses is N and D. So I'll say X is of shape N by D, meaning that N is the number of samples and D is the number of features. Okay? And so one thing that some beginners get confused about sometimes is if they took a course in the past and they used different letters, okay? And for whatever reason, they think that what they learned in their previous class was like the official world version and it is illegal to ever deviate from those letters, okay? So that's not how anything works in the real world, okay? So if you saw like N by M or M by N or, I don't know, B by D, whatever, it doesn't matter. Okay, the the instructors in other courses can use whatever letters they like. And, you even see this if you say you go to college for computer science or math and you read different textbooks for different classes. Okay, so different textbooks would use different letters depending on the conventions of that author. Okay, so this is just, something you have to learn for the real world, is different people are going to use different letters. Okay, that's a completely normal thing. Okay, so beginners, please don't get confused by that in the future. Okay, now y. So we're looking at y. Y is only one column, so it doesn't have any second dimension, but it must be of the same length as x, right? Because every input must have a corresponding target. Okay, every measurement must have a corresponding plant that it corresponds to. Okay, so as mentioned, the next step is to split the data into train and test. Okay, so we've imported a function called train test split from Scikit-Learn, and this is the syntax for this function. So if you want to look at the documentation, there are other arguments to this function that you can use, but for now, we're just using the default values. So all we need to pass in is x and y, and this will split x and y correspondingly. Okay, by correspondingly, I mean it's going to keep the corresponding inputs and targets together, okay, even though they are split up. Okay, so that splits the data. And again, we can check the size of x train and y train to see how many data points we have. Okay, so after splitting the data, we have 112 points for the train set, and we have 38 points in the test set. Okay. And so the next step is to build a model. Okay, and so in this course, we're not too concerned about what model this is. In the expanded version of the NumPy course, we also don't discuss the details of any machine learning models, but we do discuss maybe some practical ways to choose them. So like, what's the difference between logistic regression and decision trees and random forest and support vector machines? So in what circumstances would you choose which model? Okay, but for this course, it doesn't matter so much, right? We're just doing an example of the steps. Okay, that's our main purpose in this lecture, is to understand the steps. Okay, so all you really need to know is that I've chosen a model that's appropriate for doing the classification task, right? Some models are not appropriate for classification, for example, linear regression, okay? So I've chosen that for you, but in future courses where you actually learn about these models, that's when you'll learn what tasks these models are appropriate for, okay? But that's not a topic for this lecture or this course. Okay. So once we get down to these steps, you can see that previously the steps were, I guess it took a long time to explain those steps, but for these steps, they're all pretty easy. They're just one line of code, right? Build a model, fit the model, evaluate, make predictions. They're all going to be one line of code because they are already built into this library. Okay, so you can see building the model. So this is a class. This is the name of a class, and we are creating an object of this type. Okay, so the model is an instance of the logistic regression class. Okay, and then we call, on this model, we call the fit instance method, passing in x train and y train. Okay, the training data. Remember that we fit on the training data, but not on the test data. Okay, and just as a reminder of what this is doing, it's finding the slope and intercept of this line. Okay, that's basically what it's doing. Given these data points, it's finding the orientation of this line, the best place to put this line such that it fits well with the data. Okay, so we call fit. And so the next step is to evaluate the model. Okay, so this, I'll write this in a comment, this returns accuracy. And so how do we do this? We call model.score, and we're going to first try this on the train set. Okay, and this returns 98%. Okay, so what does this number mean? 98.2. So this is basically, as you recall, our model is making predictions. So it's given output, it's saying what type of plant do I think this input is? Okay, so it's predicting either iris setosa, iris versicolor, or iris virginica. Okay, and this score is the accuracy. Okay, so how many of those predictions did we get correct out of the total number of predictions we made? Okay, so in total, we made 112 predictions, and we got 98.2% of those predictions correct. Okay, so that's pretty good. But again, it's always relative. So another beginner mistake that I want to point out is sort of not understanding these numbers. Okay, so, let's say we do another example in finance, okay? And so we're trying to predict stock movements, and our model gets, say, 52% accuracy. And you might think 52% accuracy is pretty terrible, okay? But you always have to understand that this is relative. Okay, so 52% is not necessarily bad. It's relative to the kind of data you're working with. Okay, so imagine you were predicting stock movements and you actually got 98%. If anyone could do this in the real world, they would be billionaires, right? If you could predict to almost perfect accuracy the way that a stock is going to move, you could make a trade every single day and get it right and make money every single day. And because you're right so often, you can invest essentially all the money you have and basically make money every single day. Okay, and well, why don't we see people doing that in the real world? Because that just doesn't happen with financial data. Okay, so with financial data, you're probably not going to get 98%, and even something like 51% would be great. Okay, versus, it really depends on the field you're in. So you have to look at the papers in your field, what people are publishing. And so that's really your benchmark, is the other researchers that you're competing with or that are your colleagues. Okay? So you can't arbitrarily say 95% is good when your colleagues are getting 99%. Okay, but you could if your colleagues are getting 75% and you all of a sudden get 95%, well, that's pretty great. Okay, so it really depends on the relationship to what your colleagues are doing and what the state of the art is in the field. Okay, and that actually brings us to another mistake that I often see, which is, students might get, say, 75% on a data set, and then they might say, well, I want 99% of this data set. How can I do that? Of course, that's not really a question you can answer straightforwardly, right? Really, the answer to that is try everything you've learned in machine learning so far, right? There's really nothing beyond that you can do other than trying the techniques you learned in machine learning. And how do you know if it's even possible, right? So for example, with finance, we just said, nobody's going to be getting 98% accuracy on a data set where they're trying to predict stock movements, right? So if you're getting 51% and you ask me, how can I get my accuracy from 51% to 98%? That's not really a question with a straightforward answer. Okay, and so now, we've only evaluated our model on the train set, but we would also like to evaluate it on the test set. Okay, so how well does it do on data it has not seen before? Okay, and so how do we know the model hasn't seen this data before? Well, we've never passed in this data into the model, right? We've only passed in X train and Y train. Okay, so that's intuitively why the model hasn't seen this data before. So you can trust that that's the case. Okay, and so how well does it do on the test set? So it only gets 86.8%. Okay, so there's a little bit of overfitting going on, judging by this large gap in the train and test scores. Okay, so the next step is to make predictions. So now that we have a model that we are relatively confident about, let's say we're good with 86.8%, and we want to deploy this model in the real world. Well, how do we make predictions using this model? Okay. And so imagine we have some new plants that we came across in our garden, let's say, and we took out our ruler and we measured all of those 4 different dimensions that we talked about above. Okay, so we took our ruler, we made these measurements, we wrote it down on a piece of paper, and now we're at our computer and we want to figure out what type of plant did we just measure. Okay, so we'd make an array like this, and I'm just calling it X more test because it's data in addition to the tests that we already have, but it's also test data. Okay, and so notice how there are two brackets here. So why are there two brackets? And so this goes back to our n by d thing above. Okay, so you cannot arbitrarily pass in, say, if I just did this by itself with one bracket, that would be an array of size 4. Okay, but we don't want an array of size 4. We want an array of size n by d, or 1 by 4, since n is 1. Okay, so hopefully you're getting that. Okay, so similarly, you can't pass in 3-dimensional data either. So you can't pass in n by d by something else because that would also not work. It must be 2-dimensional, n by d. There must be an n and there must be a d. In this case, d must always be 4 because that's how many features we have, but n can be variable. Okay, so we can pass in 1 sample, we can pass in 10 samples, doesn't matter. Okay, so now that we have our XMOR test data, all we have to do is pass it into the predict function, and this will make a prediction, okay? And so notice how Scikit-Learn is smart enough to know to return the prediction as a string as well, because we passed in our training data as strings. Okay, and so it chooses this. I have no idea if this is correct because I just made this up arbitrarily, but now you can see how this model would be used in the real world. Okay, so for example, if you're doing email spam detection, you would plug in this model and you would detect for any new emails that come in, whether it's spam or not spam, and then do what you would with it accordingly. Okay, if it's spam, put it in the spam box. If it's not spam, put it in the inbox. You get the idea.